Over the last unit of the course, we've seen how we can write expressions that describe the rate of reaction given a series of elementary steps. So for instance, let's say we're looking at ammonia synthesis controlled by nitrogen dissociation. So our series of elementary steps might look something like this, and then we can write a rate expression that looks like this. So here we've written it in terms of the forward rate of step 1 times 1 minus an approach to equilibrium for the entire reaction. That approach to equilibrium is in turn written in terms of partial pressures of products and reactants and an equilibrium constant that depends on the equilibrium constants for each one of our quasi-equilibrated elementary steps raised to their stoichiometric numbers. To finish writing our rate expression all in terms of measurable quantities, we could write a site balance that gave us our free site coverage, and it depended on all these equilibrium constants and partial pressures of reactants and products. So the key point here is that in general, our rate equation is going to be in terms of reaction rate constants that depend on activation energies for elementary steps and equilibrium constants that depend on reaction energies or enthalpies for equilibrated elementary steps. So if we have a potential energy diagram, which we have shown here for ruthenium catalysts, both for terrace site and for step sites, we can describe the rate quantitatively. So in the next few videos, we'll see how the expression can be greatly simplified based on the fact that all the reaction energies are not independent. But first, here in this video, we want to very briefly discuss how we can actually calculate this potential energy diagram. So the information we want to build our potential energy diagram is the ground state energy of our system with respect to the positions of all of our different atoms. So this information is contained in the wave function, which we typically denote psi. So to find the wave function, we need to solve the time-independent Schrödinger equation. So this is typically written in a form that looks like this. Obtaining an exact solution of the Schrödinger equation is impossible for all but the simplest situations, since the complexity of this problem explodes as the number of electrons in our system increases. So this is really only feasible for one electron systems, so if we're interested in anything larger than a hydrogen atom, this is going to be an intractable problem. So Walter Kohn proposed a different approach for solving this problem. The theory he proposed used the electron density at any point in space as the variable of interest instead of the wave function. Kohn and others showed that the ground state energy from Schrödinger's equation, which again is the variable that we're trying to calculate, is a unique functional of the electron density, which is a much simpler function of just 3 positional coordinates. So we can write that the energy is equal to some functional f of the electron density, which is in turn a function of position in our system. So although Kohn's work demonstrated that a functional exists, we don't know what it is. So finding this exact functional is the sort of key challenge in density functional theory, or DFT. One particularly useful approach is the Kohn-Sham methodology of DFT. This involves essentially turning off all electron-electron interactions in our system, so solving for a non-interacting system, and then adding a correction term to account for electron-electron interactions. This is analogous to, say, calculating planetary orbits by taking into account just the planet-to-sun forces, and then adding in some correction factor for planet-planet interactions. In this formulation of DFT, the challenge becomes coming up with a function that describes these electron-electron interactions, which we call the exchange correlation. So development of exchange correlations is an active area of research, and typically these exchange correlations are optimized for certain physical situations. The development of DFT and increases in computational power have allowed us to simulate reactions entirely on the computer. So we could calculate the adsorption energy, for example, of a molecule by using DFT to calculate the following energies. So the potential energy of adsorption, which is closely related to the enthalpy of adsorption, would be equal to the energy calculated for our molecule, let's say A, attached to the surface, minus the energy of the molecule moving around freely in the gas phase, minus the energy of the bare surface alone. We could also calculate energies of reaction. So if we wanted to calculate the energy of reaction for a Langmuir-Hinchelwood type step between an adsorbate A and an adsorbate B, we could simply simulate the energy for a system that looks like this, where we have A and B together as a product on the surface, minus the situation where they're separate from one another. Mathematical methods also exist for searching for the minimum energy pathway between stable reaction intermediates, and if we find the maxima along these minimum energy paths, these are our transition states. So in this way, density functional theory can calculate activation energies as well. So in this way, we can calculate entire potential energy surfaces for our reactions, which we can use to describe rates quantitatively. We'll also see how the ability to calculate large number of adsorption and transition state energies quickly using DFT has given us new insights into understanding catalytic reactions.